Hi everyone, my name is Amanda Gregg. I'm a material science and engineering PhD student at Duke, and today I'm going to be talking about my research in creating an energy efficient incandescent light bulb. But first, I want to talk about our current indoor light sources, beginning with the very familiar incandescent bulb. And incandescent bulbs are really well loved because objects, when viewed under them, are viewed very true to color. And we call this having a high color rendering index, abbreviated as CRI. However, incandescent bulbs have been phased out due to their high inefficiency because most of the emitted radiation is lost as heat. So we now have LEDs. But LEDs have their own problems. They're made from rare earth elements, and when these are mined, it creates chemical waste streams as well as greenhouse gas emissions. Additionally, these have a comparatively lower CRI. Therefore, we would like to make an ideal light source that is made without rare earth elements, that's efficient, and also has a high CRI. And we would like to do this with metamaterials. And metamaterials are basically materials comprised of arrays of these very small structures that are the artificial atoms. And when you change the geometries of these artificial atoms, you can change the bulk electromagnetic response of the material. This application, we are specifically interested in dielectric metamaterial absorbers because you're able to get perfect absorption at some target wavelength frequency shown in this figure. And via Kirchhoff's law, that also means that we have a perfect emitter at that frequency. And if we consider black body emission, which we would like to have for an incandescent light source, we can essentially modify that black body emission by multiplying by this specifically designed absorption of the metamaterial. And this is shown here that by multiplying these two plots, you're able to get something that we call the gray body emission. Is basically, you can see you're just shifting the peak of that black body emission. And for a light source, we would like to shift the emission of a tungsten bulb to match the sun. The sun is a very natural light source for us, and it is also output entirely in the visible. So this is shown by the figure here. Kind of where that rainbow is where human eyes can see. So as you can tell, we would like to move that tungsten curve to match the sun, but really only the wavelengths to which human eyes can see. And this gives us our target spectrum. This is known as a truncated black body. Now we have our target spectrum. We want to go about designing the geometry. And since this space is so huge, we cannot possibly simulate all possible designs. So we have to employ machine learning, which we do in the form of deep neural networks. This starts with the forward model, which, shown by this first equation here, learns the relationship between the geometry and output spectrum based on a training data set of simulation data. And then once this model has been trained, we fix it and we provide it the target spectrum and allow it to predict a geometry. This is the inverse problem, and this is really what we want from our neural network. So for this problem, this is what the results look like. As you can tell, the gray body spectrum from the metamaterial very closely matches the target spectrum. So now I want to show an animation of some other designs that are not as good that the model was able to identify as not as good. And as you can see, this kind of runs through these other designs, and the model was able to select the geometry that gave us the best spectrum shown here. So we were able to achieve everything we sought out to achieve. No rare earth elements were used in this design. We have a near perfect color rendering index. We also have a luminous efficacy, which is the figure of merit for lighting devices that is comparable to that of LEDs. We were able to achieve all of these things while also making an incandescent light source that is 10 times as efficient as the typical tungsten sources that we're used to seeing. So now that we've designed this metamaterial, last thing to do is to fabricate it to make this device a reality. So lastly, I just want to acknowledge my funding and my support and advisement for this project. If you have any questions, feel free to reach out to me. Thank you.